Frazee, and this is your unit assignment to build the stationary tooling for all the lathe operations. So the nature of a lathe, basic lathe, is that the tools are fixed. The material is spinning. And so if we take a look at a standard CNC lathe here, here's an example of the lathe I have down at Charles A. Jones. So the material clamps in the chuck here, and then this part of the machine here is called the turret, and you can see a couple tools sticking out from the edges, and this turret moves and engages the fixed tool with the spinning material and creates the cuts that you want in the material. So if we're to look at another angle, this is the front of the turret, and this one's empty. It doesn't have any tools, and we have 12 positions on this particular machine. And so that's what we're going to model our assignment around. Is you're going to figure out which tools are going to go in which position and build your tool library for HSM. Don't worry, I am going to give you lots of help here, and we should have something that looks similar to this. This is a different lathe with a smaller turret, but what we have here is two different types of tools. We have these tools that are pointing outwards from the center of the turret. Those are radial tools, so they cut on the circumference of the material, and in this case they're all outside diameter. And then we have these drills and taps and mills that point in the same axis as the spindle, and those are called axial tools. So the turret will position so that this tool is on center line of the z-axis, and it can only do operations on the center line. This is in a traditional fixed tool lathe. Now there are more advanced lathes that will be covered in the next class, and those are called live tooling, where these tool positions with the rotary tools can actually turn on and spin, and in that way they can do their routines in places where they're not on center line. And so they cut flats or hexes or slots in the cylindrical pieces. Okay, so we may be returning to this image a few times just to kind of get context of what we're doing. Okay, if you go to your Canvas assignment, you should be able to find a PDF that looks like this. And I went through and I reviewed all the drawings to try to review this as a manufacturing engineer, looking at the family of parts and trying to reduce the number of tools that are used for the entire job. So I have a column here that says used on part numbers, and that particular tool is used on every single one of the part numbers listed there. And what we do is we put our most common tools at the beginning of the library, and then at some point, because we have a total of 20 tools, we run out of room in the magazine. So in the turret. Okay, so the least frequently used tools, which happen to be in this family of parts, are drill bits. They're going to use the same tool positions, but we have to make sure the correct tool is in that position when we run the program for the appropriate part. So for example, if we look at position 9 is going to be used for these three part numbers with this particular drill bit in it. But when we put in the dash 107, we need to swap that drill bit out for a different one. And and then we get up to number 12, which is really only used on one part, but it's a special tool and it's used on the most complicated part. So we use pretty much all 12 positions to make the primary cylinder part, the dash 101. Okay. So what we need to do is build these in Fusion 360. And what I've done for you is I've put some of the basic dimensions. Over on the right is the tool type. The blue numbers are actually the MSC tool numbers, order numbers for the items. And we should be able to pull any information I didn't put in the spreadsheet from their catalog descriptions. And over on the left we have a description of the tool. They're a little bit long, and some of them use these standard abbreviations that are a little cryptic, but we'll work through it. We probably don't need to use the entire description we have there in HSM. And then over on the right, some of them I've added the tool holder, because some of the tools, it's helpful to have the tool holder geometry. It asks you for that. And so we're going to work from that. And we have the brand, and then we can actually, so again, if you pick on one of these, you can follow the hyperlink and it'll take you to that particular cutter insert. Okay, that's a cutoff insert. All right, so some of this we'll be learning about the tools themselves. All right, so let's start with tool 1 on our list. And tool 1 is, it's a neutral indexable grooving blade with an ISCAR insert that is 1.575 wide. And so we have a cutting width of that dimension. And it's a blade, and then that blade holds this insert. So let's look at the blade real quick. So it's this flat blade looking part, and what it does is the insert gets captured in here, and it can be used like almost like a single tip saw. As the material's turning, it'll cut the material off. And it has two sides, so when the one end is worn out, you can flip it over. And also the insert that goes in there also has two sides, so you really have 4 cutting edges you can use before this thing's worn out. Alright, so let's go back to SolidWorks, and we're going to go to the tool library, and we're going to create a under my libraries, you're going to create a new library, and let's call this the S60 lathe tools. Okay, so all the lathe tools are going to be in this library. Okay, and we're going to create a new turning tool. This gives you general information. So, okay, it's going to be tool number 1. It's going to have a compensation offset of 1. And it's in our primary turret. Our description. So let's go to our description in our spreadsheet. We're going to grab this. We're not going to use all of it. We're going to do a copy. Do a paste. So we're going to call this a DGFH neutral blade. And we're going to delete the company name, and we're going to delete insert. Let's take indexable out, and we're actually going to put the dimension first. Okay, so we have our width and the type of grooving blade. Okay, here we're going to put ISCAR. So under the product ID, we're actually going to put the insert number. So let's go back to our spreadsheet. So let's go ahead and pick on it. It's going to come up with MSCs. And we're going to just grab the URL with the part number on it. And we'll go back and put that in as the product ID. And that way we can go and actually buy that insert. So we're going to change it from general turning to grooving. Okay, and we're using a square version. And our units are inches. And we need to go back to our catalog to get all this information. So we do know our groove width was 0.1 575. Okay. Okay, we're going to get our corner radius. So if we go down to the specifications, corner radius is 11 thousandths, 8 tenths. Our overall length in inches is 0.7402. We'll copy that. We're going to put a head length half of what the overall length is because the insert flips over. So that works out to 370 thousandths. And on thickness, let's put 300 thousandths. Okay, so let's stick with that. Okay, we're going to go to the holder. Grooving, external grooving. It's going to be actually a neutral cutter, so it's right in the center. And the shank width is 0.126. So it's a blade, it's not actually a big holder. Our overall length, dimensions for the blades, the shank height was 1.26. And the overall length, oh, it's 5.96. Okay, so our head length is going to be 2.98, just half the overall length. So half the blade would have to be inside the holder, and the other half sticks out. Now, they said that in the catalog that this had a maximum turning diameter of about 2.3, and the largest thing we're going to turn is 2 inches in diameter, so that should work out just fine. Okay, now we're going to go to setup. And what's the orientation in the turret? It's going to be facing the spindle, and it's going to be cutting when the machine is in forward, which is counterclockwise. And then feeds and speeds, you can set a default feed and speed for this cutter. So we're going to say our stock diameter is it won't be any bigger than 2 inches. And what we want to do on a lathe for a radial tool is use constant surface feed. So what it's going to do, it's going to vary the RPM based off the diameter. So as it gets smaller and smaller, it's going to speed the spindle up. Okay, and so we're going to leave the surface speed at default there. And you have the choice to do it in 2 different methods. You could do cutting feed rate, where you can check this box and do it in feed rate per revolution. For this, we're just going to leave it as is, and we're going to accept that. We're going to hit OK. All right, we've built our turning grooving tool. Okay, so we have our first tool in the library. Okay, let's take a look at what we've done here. So we just created a blade style groove tool, which is represented on the tool on the far left. And but there's different styles of groove tools. The one we've chosen to do does deep cutoffs and facing. Some of the others are better at turning sideways, like the two you see from the outside diameter. They're on top. And then there's also inside diameter grooving tools that come in different configurations that are designed to go inside holes. The third type is on the far right, and it's designed to do grooves in the face of a part so that the groove itself is cylindrical on a flat plane. Now let's take a look at a traditional insert cutting tool. This one could only cut smaller diameters, but it's a carbide insert, and oftentimes coolant is designed to go through the cutter. And so the very tip cuts as it goes through the material, as you see in the slow motion. Here's an example of a cutoff tool. Here's an example of a face grooving tool. It's grooving in the face of the bar. Here's an example of a grooving tool cutting into a hexagonal shaped bar. You get an interesting visual illusion. It appears like it's changing directions, but it's not. So as it engages the workpiece, you hear the interrupted cut kind of growl at you, and then the piece pops off. Here's an example of a external grooving tool, just doing grooving. Not designed to cut the entire part off. And here's an example of a grooving tool that's designed to turn also. It has a circular insert in it, so it can cut side by side, but the profile is a curvature. So these are pretty handy for replacing several different tools, and you don't have any transition marks between one tool to the other. Okay, so let's go to our next tool. We've got description. It's a 1/2 inch diameter, 90-degree spot drill. Okay, and it's Micro is the brand. It's a 1/2 inch diameter. Its shank's a 1/2 inch. Its overall length is 2.5 inches, and it has a 90-degree tip on it. Okay, so let's go ahead and look at what that tool looks like. Okay, looks like this. Stubby, nice and stout. Let's go to our HSM, and we're going to add that. Okay, so now even though we're using this on a lathe, drill bits are considered mill tools because it's a rotary tool in design. So we're going to pick on mill tools, but we're going to change our type to a spot drill. Okay, which looks kind of like what our drawing did. And our tip angle is 90 degrees. Our diameter was a 1/2 inch. Our shaft diameter was also a 1/2 inch. Our overall length, so that means our flute length is 1 inch, which is what our drawing says. And if we have an overall length of 2.5 inches, well, let's say it's 1.5 inches. And then our shoulder length, we don't really have a shoulder because the diameter doesn't change, is also 1.5 inches. So now we're going to go to the shaft, and we don't need to change anything here. Go to the holder. We could add a holder. We're going to put this in a ER32 holder. So let's just select one if we can find one. ER32. Okay, we're going to select it. Holder geometry, we're just going to leave that at default. Feed and speeds, again, we're going to leave all that at default. 5,000 RPM is a little high. It's 2 flutes, not 3. Retract is fine. These feed rates on a lathe are not going to really output. They're just going to output in rapids. Okay, we're going to hit OK. So we have our 1/2 inch diameter spot drill as number 2. Now let's look at how this drill bit would appear in the turret. So it's an axial tool, and so it'd be sticking straight out. And it's more or less like the tool that you see currently in position 5 or 4. I'm not sure which one is. I'm not familiar with the Tormach machine. But the drill bit that's sticking out. And it'd be an ER32 collet held by a boring bar axial tooling block. Okay, now let's move on to the next tool.